unless there is pleasure in the work, no matter how much salary you get, it won't matter. The growth of civilization is in the hands of material scientists. Today, India is, and quite proudly, the second largest steel producer in the world. So I wrote to Dr. Irani, who was the managing director of Tata Steel, expressing my desire to join if they find me suitable and attach my CV. There was no interview. 5 days later, I got a faxed appointment letter.
As a child, I would watch these ads that says, we also make steel.
Mr. Tata said, this is a very good idea. But then why have you taken a 7-year-old car? He said, I've just gone into the Toyota factory. They're making on the lines, they have a new model coming out. Get one of those and cut it up.
We know how to make steel. You know how to break steel.
Yes. It is important for the material scientist to be trained in AI.
Yes.
Because you can't train a data scientist in material science.
Namaskar and welcome to another edition of the Professor Mahesh podcast. This is your resource to help you make informed career decisions. This podcast is brought to you by IIT Madras Global, an initiative of the Office of Global Engagement at IIT Madras. IITM Global is our platform to help take IIT Madras to the global stage, our startups, our thinking, our teaching, our research, our philosophy broadly. Come learn more about the initiatives of IITM Global in the links in the description. For today's conversation, I'm delighted that for the first time for this podcast series, I have a person with a strong industry linkage, the first guest of mine with an industry stripe, and one that I thought was absolutely essential given the field we're going to talk about today. Metallurgy, metals and material science. I'm delighted to have Dr. Debashish Bhattacharjee here with me. Debashish is currently a professor of practice at IIT Madras, formerly the Vice President for Technology and R&D for Tata Steel, and also currently is the managing partner for a new deep tech fund called Lionstead Ventures. Learn more about these funds because these kinds of funds are important to grow deep tech startups in the country. For today's conversation, we need to understand that metals, in particular steel, is at the core of the growth of any country. For a large growing country like India, our own steel footprint and broadly our own metallurgy footprint is practically going to determine the growth trajectory of the country. I've always thought that the growth of any country comes from only two places. One is the ore that comes out of the ground and the food we grow in some sense, and the ideas that the people bring to the table. In all three of these, India is growing, and today we're going to talk about the future of metallurgy, material science, and metal making broadly in India. Welcome, Debashish. It's a delight to have you here today.
Thank you, Mahesh. It's a pleasure to be here. It's an honor to be here. And thank you for giving me this opportunity.
The honor is always mine. Let's start with steel.
Sure.
Steel is a metal that we can't live without. I mean, it's absolutely essential for the growth of the country. Where is India today in steel production? And where do you see it? Is it sufficient? Are we there? Or do we need to do more?
Yeah. See, human civilization is sort of road-marked based on materials. Civilization had the stone age, then copper age, and eventually iron age. So we are sort of, and then silicon age. So in terms of hardcore construction, stone construction, copper went into construction, and weapons, and steel, iron and steel eventually is construction. So the civilization we live in today is built on a bedrock, if you wish, of iron and steel. Wherever you look, whether it is bridges, railways, whether it is buildings, name any construction, steel is essential. In a way, the extent to which a country has matured is in a way measured to which it uses steel. So more matured countries use steel to the extent of about 400 kilograms per person per year.
Okay.
Just keep that number in mind, 400.
Okay. Almost half a ton.
Yes, yes. When China was in its rapid growth phase of nearly 3 decades, and even now, it was using about 700 to 800 kilograms per person per year.
Wow.
That's a measure, and it shows in outwardly in the way a country develops or the state at which its development lies. Which brings me to the second part of your question. Today, India is, and quite proudly, the second largest steel producer in the world. World makes about 1.8 billion tons of steel. Right? That's 1,800 million tons, roughly. About 1,000 million tons is made in one country called China. India makes about 150 odd million tons of steel, and it's number 2.
Wow.
So that's the difference. But then proudly, India has grown rapidly over the last 10 years to be number 2, beating the so-called majors, Japan, US, and EU. So it's now number 2. Now, hard back at the number I said earlier, 400 kilograms for a developed country. China at about 700, 800 kilograms per person per annum. India at 150 million tons of steel production. That number is roughly 150, 145 kilograms per person per annum. India is on a development spree, right? And India will therefore grow to the extent of about consuming 300, 350, eventually 400 kilograms per person per annum, right?
This probably in 15, 20 years?
In about, yes, because it's not easy to put steel production capacity. It's capital intensive. It takes time. It also needs the market to grow. Indian market is growing, and if you look around, Indian steel companies are busy spending capital in putting in new plants. So we see India growing to about 300 million tons by maybe 2030, 2032, and then growing on to about 400, even 500 million tons of capacity by 2040, 2045. It needs huge capital expenditure. But then the market pull in India would be such because of growth that it will pull that, necessitate that expenditure. So we are number 2 in the world, to answer your question, in steel production, 150 odd million tons. We clearly see the writing on the wall to grow to 300 million tons, and then from there on to about 450, 500 million tons by 2040, 45.
Wonderful. How did you become involved with steel? What was your journey? You started at Jadavpur.
Yes.
I consider it the pride of India.
Thank you. So my bachelor's was from Jadavpur, which in a way shaped my thinking in metallurgy. Right. I came into Jadavpur not knowing much about metallurgy. It is like many in my generation, that's what I got, right? Because that was the score, and I wanted to do engineering. I wanted to do in Jadavpur, and metallurgy was available. And frankly, I was happy I got into metallurgy. But when I went into first year and got the first lessons in physical metallurgy, was taught dislocations, and I got to know how plasticity happens in metals. That was exhilarating. It was a confluence of physics, chemistry, and real forming of metals. Right. I fell in love with metallurgy and materials in Jadavpur. I went into a job for 1 year, but I completely abhorred it. I said, this is not my calling. I went on to do masters at IIT Kanpur, and I was very, very fortunate to have excellent supervisors and to courses in dislocation and further physical metallurgy there. And I was fascinated by fracture mechanics. which led me on to University of Cambridge, where I did my PhD in fracture mechanics at the Metallurgy and Materials department. Stayed on to do my first postdoctoral at the Rolls-Royce Technology Center in high temperature fatigue. So was thoroughly conversant on materials failing, and we were called the crashers and bangers of the department because that's what we did.
And it's not easy to break a piece of metal.
It's not. So you need techniques, and more importantly, when you break them, you realize how you develop materials and in all sorts of materials, metallic, non-metallic materials, to withstand the test of time, to withstand to be structurally integrated and to withstand failure modes. So in a way, I became conversant with physical metallurgy and mechanical metallurgy of number of materials. Started with steel, had aluminium alloys, and even polymethyl methacrylate, PMMA.
Yeah,
because it's from a fracture mechanics point of view, it's an ideal brittle material.
Correct.
Right. But at that time, when I had spent about 8 years in Cambridge, I decided that my further career has to be in India, not outside India. We decided to come back. And here's a bit of a Tata story. So I was, as usual, when people apply from abroad, I was applying to all the IITs and was getting response. When you come to India, come to us and give us a talk. We will assess. So I was clearly saying 6 months due time. So somebody said, "Why are you only addressing universities and IITs? Why not industry?" I said, "I don't know any Indian industry." So Tatas have a very good steel company and very good R&D in Jamshedpur. So why don't you write to them? So I wrote to one. I didn't even know he was a doctor. I wrote to one Mr. J.J. Irani, Dr. Irani, who was the managing director of Tata Steel, expressing my desire to join if they find me suitable and attach my CV. There was no interview. 5 days later, I got a faxed appointment letter.
Wow.
Now, yes, I said, wow. And that
Which year was this?
This is 96.
Okay.
I got the appointment letter in 95. I wasn't ready to join. So, but then this is what attracts people to institutions, right? That they want me.
The alacrity with which they moved.
Exactly. Yeah. They said, when you have this CV, when you have this background, many people do apply, I'm sure.
Sure.
But the fact that they expressed the desire, that they wanted me was the glue. And then it doesn't matter, how much they pay or what rank they take me in. And I was so glad I said yes to that. So I joined 6-7 months later. In the meantime, I had the opportunity to meet Dr. Irani in London. And it was not an interview because they had already given me that we had crossed that bridge. So he asked me many questions about my life, my family, and I asked him, "Why have you taken a fracture mechanist? I have not done hot rolling, cold rolling, or coatings." And there came an answer from him. He said, "We have a lot of metallurgists who have done steel. You have a broad background, and we want to broaden our horizons." What a great answer.
We know how to make steel. You know how to break steel.
Yes, or prevent it from breaking.
Sure.
Yeah. And they said, "What do you want?" I said, "Look, I don't know how much you pay and what does it mean when I've been living here." So I just, in the passing, I said, "Look, he did his PhD in Sheffield, and you've lived here, so you know what the quality of housing is. And a decent house would be good to have."
Sure.
And that was it. 7 months later, I land up in Jamshedpur. And usually when you land up, you're taken to the guest house. I was taken to the guest house. And the next step is to look for a proper housing for you. Yeah. So they went around looking for a proper housing from me. The first step was to go to the HR department, and there's a register. And according to your marks, the mark here is 0 because I'm a new entrant. There are certain levels of houses.
Sure.
And the person who was sitting there, he jumped up. He took the whole register inside, obviously, to his boss. And then his boss came on and said, "Who did you meet?" I said, "Nobody. I'm just coming from the guest house. I just landed in Jamshedpur." "No. Who did you meet earlier?" "I met once Dr. Irani." Dr. Irani is noting is here. And this house is already allotted to you. And it was a very senior level house. And when we finally moved into that house, we realized that the people who stayed there, their children were of our age.
Wow.
So it was obviously meant for very senior people. But the point is that a remark in passing in a conversation was taken so seriously that I didn't have to follow up. A house, an appropriate house, I don't know.
Sure.
As far as I was concerned, very appropriate for me. But clearly, very senior person is eligible for that house. Not
Tatas are known to take care of all of their employees.
Yes.
Very well, aren't they?
Yes, absolutely. And I just narrated 2 episodes to you, two experiences of mine. Another one, just to highlight that, my father had just passed away in 2003, and I was at home for the Kriya Club and all that in Calcutta. I was based in Jamshedpur. I got a call from the then managing director, Mr. Muthuraman, expressing his condolences, and he said, "Do you need anything from us?" I said, "No, thank you very much for that, but I don't really need anything." So he put the phone down and he called back again. He said, "Debashish, you will need a car to go around in this time, and I don't want to hire taxis and stuff. So I'm asking my office to just let you use a car for however long you need." He didn't ask me whether I need. That's the level to which, the detail to which senior management looks after people.
So touching. I will add my own little Tata story, even though I've never had the good fortune of working for a Tata's. But as a child, I would watch these ads that says, "We also make steel."
Yeah.
Right? And I had to grow up to really understand what it meant. But I can now see what they mean by "we also make steel."
Exactly.
Right? So that really sums up the mentality or what should be the makeup of a good, large company.
Absolutely. And it is not only, if I may take 2 more minutes to give you a technical example, and these are all personal examples. It is not only heartwarming, it is also inspirational. Back in 2003, 2004, we came up with this idea that, India was making its own cars, or even the Japanese companies were coming into India making cars. And the steel companies were still not sure what steels to make, what goes into a car. So we decided to buy a car and cut it and see what steel goes where, right? And we were in R&D at that time, young researchers. We didn't have the gumption to buy a new car. So we bought something that was second-hand. One of the senior officers had which was already used for about 7 years. And we cut that car up and we did a very nice report. It was presented by Dr. Mukherjee, who was then Deputy Managing Director, to Mr. Ratan Tata, who had come to Jamshedpur. Mr. Tata said, "This is a very good idea. But then why have you taken a 7-year-old car?" He said, "I've just gone into the Toyota factory. They're making on the lines, they have a new model coming out. Get one of those and cut it up." We were just waiting there to be chided for the fact that we wasted money in cutting a car off. He said, "Buy a new one and cut it off." That's inspirational.
It is.
Yeah.
It defines the philosophy in some sense. I think steel making in India largely has been associated with either Tata Steel or SAIL and other public sector steel makers. In the last 70 years of steel making, we've come a long way. As you said, we are now at about 150 kg per person
per annum,
while the population has grown, fourfold in that same span of time. Let's talk about other metals, and we'll come back to define the problem more broadly. We want to talk about steel, which is one of the key metals, and other metals, metallurgy and material science. Let's start with material science. Okay, what's defined as material science, and what does a material scientist study?
To me, anything that is tangible and comes to the use of humanity is material, tangible, right? So this table is material. The microphone in front of me, the diaphragm that's vibrating, is material. The armature that's holding it in place is material. there's a huge debate that goes on between metallurgy, materials, and what should be taught, what shouldn't be taught, what should be subservient to the other. In my opinion, metals, non-metals, all are part of materials. So I have no issues in putting iron and steel under materials.
Okay.
They're all materials. Some happen to have different characteristics from the others, but materials is a broader aspect of all tangible substances that we use in common, that is in common use today.
Mm-hmm.
What we study is essentially how to make the right material for the right use.
Mm-hmm.
Right? I'll take an example. Airplanes were made with aluminium.
Mm-hmm.
Yeah, light metal. You wouldn't think of making airplanes with steel.
Mm-hmm.
That's not the right material. Its density is high. It corrodes. You make it out of stainless steel. It's too expensive. High density. You make it out of aluminium, which doesn't corrode, is lighter weight. You can rivet pieces of aluminium into place. It's quite solid, right? But as you go to larger airplane bodies, as you go to lighter bodies for less fuel consumption, you look for different materials for that use purpose. So aluminium gives away to carbon fiber, or maybe a carbon fiber combination with titanium, right? Because carbon fiber doesn't go well with aluminium. There's a huge corrosion issue, right? So external issues like fuel saving, lightweighting, dictate use of materials, choice of materials. Therefore, as the need to reduce fuel use, and therefore go to lighter weights in planes became stronger and stronger, the search was on for an alternative to aluminium. So all the new large body planes that you see are a combination of titanium and carbon fiber, right? Mm-hmm. So all these are in material science. How do you find a material that's right for the use case that is being thought about? Mm-hmm. Today, you're talking about quantum, right? Quantum computing. Now, you're going to smaller and smaller sizes, right? In the nanometer scale, even if you cross the 22 nanometer size, you can no longer use silicon as a gate. You have to go and find another material. So it becomes a material problem. So whether it's a plain body or whether it's a gate in a semiconductor, these are all materials problems. Some electronic properties, some deal with mechanical properties, some deal with chemical properties, some magnetic properties in motors, for example, right? So underpinning everything that we do in day-to-day life is materials. And I would put all of these together under material science. Mm-hmm. And I think study of a broader aspect of material science is very important, because the student comes out knowing, being given a holistic picture of materials, right? Not just iron and steel, or not just aluminium, not just plastics or silicon, right? Gets a holistic picture, and therefore, right from formative years, has the mindset of choice of materials, right? Whether it's aluminium or steel, whether it's silicon or something else, or graphene, or whatever. That materials are a matter of choice for a particular use. That is what material science education should be.
So it's sort of like a use-inspired quest for the appropriate material is never going to stop.
No.
So there's always going to be room for a material scientist in every project imaginable in the future. Forever.
Well, even in the Stone Age, I'm sure there was a good stone and a bad stone for a particular use.
There was a material scientist back there.
There was a material scientist back, and it was a material scientist who put copper into use in place of stone.
Wonderful. So I think, would you expect a good material scientist to sort of be walking around with a little library of materials in their head, or is there a better way to parse the problem?
There's always a better way to pass the problem. Material science is like an encyclopedia, right? And today you have artificial intelligence and machine learning, which can look into all data that researchers and people in industry have generated in making these choices of materials, in developing newer and newer chemistries, combination of chemistries, alloys and composites, and use AI ML techniques to search for the right combination for the right usage. So there is a huge role of AI ML in metallurgy for making rapid choices in developing new solutions for
We'll come to
application.
that. I'm sure we'll come to that a little later. Let's now, if there is a reason to sort of parse metallurgy
Yeah.
from material science. What's fundamentally metallurgical engineering?
Okay. Although I do believe that they both should be taught together, but metallurgy is about metals, and essentially, it's about extracting the metal from the naturally given ore, right? And then processing that metal into shapes and sizes for final use. So, for example, iron ore. Metallurgy involves choosing the right iron ore, upgrading it to the right concentration, then putting it through furnaces to extract the iron from the iron ore, then refining to the right quality, and then hot forming, cold forming to the shape that you need for making a car, for example,
Okay.
yeah, or a bridge, for example, or a train, for example, rails, for example, right? So that is metallurgy. Involves mineral beneficiation, involves chemical engineering and chemical processes for extraction, involves mechanical forming of the materials, involves deep study of lattices and how lattices change, crystal lattices change in the material during physical mechanical forming of the material, and therefore once you've understood that, you design the lattice structure in such a way, and the constituents of the lattice structure in such a way that you get the right hardness, right strength, right toughness, right plasticity in the material. So that's metallurgy.
Okay.
Material science is mostly to do with non-metallic alloys and materials, whose raw material source is not necessarily from the ore, and they're not necessarily dealing with structural properties. They're dealing more with functional properties, such as electronics, such as packaging properties. Traditionally, these two have been kept apart, right? But I do feel that there is no reason for these to be kept apart, right? Why would a person who's doing metallurgy for electric vehicle motors not know how electricity and magnetism is influenced by the size of material in the stator? Traditionally, I would put a sheet of steel in the stator, but we don't need to put a sheet of steel in the stator. We can put a powder in the stator.
Correct.
To think in those terms, you need to break the silos between metallurgy and materials.
Very nice. Let's talk about metals.
Yeah.
We talked about steel and where India is. The three most commonly talked about metals are iron and iron alloys, steel included. Then aluminum. You alluded to aluminum, and nickel alloys.
Yeah.
And there may be others. Are these roughly the three?
Of course,
The three
yes.
most important classes of materials. Let's talk a little bit about aluminum. Where India stands in aluminum, and what is the prognosis there, and if there is a way to talk about other alloys,
Sure.
we could broaden the discussion as well.
Sure. Since you mentioned aluminium, India is the third largest producer of aluminium in the world. It has huge deposits of bauxite. It has capacity to process. It has capacity to make final products. It produces what is needed by the Indian market.
Okay.
Right? And as the Indian market changes, I'm sure the quality of that product or the grades of those products will also change. And the same story holds true for steel, right? Indian steel industry and aluminium industry don't necessarily produce the grades that are considered to be very high end, right?
Okay.
So, for example, even for automotive steels, the higher end, high strength grades are not produced in India, right?
Even today.
Oh, even today, yeah. The high end grades that are produced by, say, Nippons or the European steel makers are not produced in India, right? Partly because the Indian market never needed those, they never demanded those. So, and in industry, it's always a demand based development. European and Japanese car makers, they demanded those grades. So the development happened. And I'm sure if the capability exists in terms of intellectual capability, the capability exists. And I'm sure when the market develops, Indian market develops, Indian production will also develop. The same story is valid for aluminium, right? The grades and the quality that's produced by, say, the European aluminium manufacturers is not produced in India, right? And again, I can use the same logic as I used for steel. Nickel is different. India does not have much nickel deposits, right? And traditionally, India has not paid much attention to garnering those resources from abroad and having processing capability inside. We have never thought of it like that. Other countries have. So they have not worried about not having their own resource. They have obtained those resources and brought the ore and or the intermediate and processed internally, right? We have not done that for nickel. We have not done that for cobalt, for example, and most of the other critical minerals, right? It has now dawned on us that this is what is necessary, right? We need a lot of nickel. We need nickel for defense. We need nickel also for batteries, for energy. Right? It goes into battery material.
Sure.
Which brings me to another point, which is you in your opening statement, you had said that there are two things you consider of primary importance, which is agriculture and natural resource. Right. So when we come to critical minerals such as nickel, or such as even titanium or cobalt, I'll keep titanium aside. Titanium is a different story. We have a lot of titanium, but other minerals such as cobalt and all that, we don't have the natural resource. We don't have enough natural resource. But then gradually we should think of recycling the secondary availability as resource. So progressively, urban mining should be seen together with natural mining.
Is that technology underpinning urban mining fairly well developed, or is there room for a smart group of people to step in and help?
The technology for urban mining is understood.
Okay.
Proof of concepts exist. They need to be upscaled.
Okay.
India has, I think, now quite an active startup ecosystem, or even an SME ecosystem in recycling of electronic waste. Recycling of battery waste is just starting. But those are usually with traditional technologies of a type of metallurgy. And here metallurgy comes in deeply, right? So I'm going to use some terms which will be good for your viewers, I hope. Hydrometallurgy and pyrometallurgy and electrometallurgy. So it's metallurgy using water and solvents and pyro.
These are all ways to recover.
These are all ways to enrich and recover.
Would this apply across, like, say, a class of metals and rare earths and such? Or?
Across. So, but you would need the right combination at the right stage. So there would be steps in the manufacturing chain, if you wish, of, say, battery recycling of batteries, or in recycling of electronic waste. There will be different steps. But fundamental metallurgy combinations would be the same, hydrometallurgy.
And clearly this is a problem for us in India.
Yes.
But a person who becomes well-versed in this is a global citizen, ready to
absolutely
to move on the global stage, because these are world pesky problems.
We see that in the next 25, 30, maybe 40 years, 50% of our resources will come from recycling, urban mining. And the remaining 50% will be natural. right? So it will be so important to have this capability with us that will be really valued across the world.
A student wanting to head in this direction would start in a metallurgy or a material science program. Are there, you think, master's level programs that would train the student in this
Sure.
direction? Where would they get started and go?
Sure. It would help if they do a metallurgy undergraduate, a metallurgy materials undergraduate,
Okay.
right? They get the fundamentals. Most metallurgy departments in the country, some are called metallurgy, some are called metallurgy materials, some are called only materials, but it doesn't matter.
Sure.
Most of them would have a course in extractive metallurgy at the master's level, right? And this is where they would be taught this. And if they're not, I would suggest that the institutes wake up and make this as part of their master's curriculum to teach deeply these subjects.
I also know there are multiple NPTEL SWAYAM courses
Yeah.
On extractive metallurgy
Yeah.
that students can use to get started.
Absolutely. And for engineers and even scientists from chemistry and engineers from chemical engineering, metallurgical engineering, even mechanical, they would immensely benefit by being relevant to the world of the future by taking these courses.
Let's switch gears and talk about alloys.
Right.
There's these routine run-of-the-mill alloys that are used in large quantities, which I'm sure India is doing okay. But there are specialty alloys which are of strategic importance to the country. And, we end up importing strategically important materials. What can we do? What can young men and women do to sort of say, I'm going to try and see if I can solve the problem?
Yeah.
First, let's define the problem. What are some specialty alloys that are important for a country like us?
So there are clearly a set of alloys that are used in defense, aerospace and defense. Turbine blades. Yeah, they are nickel-based super alloys. Alloys that are resistant to piercing bullets and shells, and alloys that pierce more effectively, on the other hand,
Sure.
in defense. But even in normal day-to-day use, you need special alloys for very high-frequency, high-efficient motors. So motors that rotate at greater than 1,000 RPM, they would need special electric steels, which are special silicon alloys. Even transformers would need special alloys, which India doesn't make today. There are two things that need to happen. Whenever India has seen that make is a better option than buy, or the buy option goes away, India becomes very good at making. And we have seen in atomic energy, we have seen in our space program. So when the door closes because of geopolitical reasons, we beat the world by making our own. And I think this is where we are seeing geopolitics change today. Where we're quite easy to buy are not so easy to buy today because of the reasons.
Yeah.
And I think this is what our younger generation should be aware of, that opportunity is coming to India of making those alloys ourselves for our own needs. When we didn't have the opportunity to buy atomic energy technology, we developed our own atomic energy technology. And that's history.
It is.
Right? So we will have our own alloys without depending on imports and without depending on knowledge and technology from outside. Because the Indian institutes have all the wherewithals to teach, to do research. We just have to be directed to do research in the right way and to the right goals. And the goals are now opening up. So I think the younger generation today should be aware of the fact that the geopolitical situation is working actually in favor of India. It is, the more it closes the gates for imports, the more is the opportunity for us to develop our own alloys for those critical needs. India has the infrastructure. India has the knowledge in its institutes. It has the professors who have the knowledge, who can do the research, who can guide the students, and and we can do exactly what atomic energy did for India, or ISRO did for India.
When I imagine, a steel making plant or an aluminum plant, I'm imagining massive quantities of steel and aluminum or any metal being made, by the day, massive infrastructure. Are specialty alloys different? I'm imagining, can a small group of people create a startup around a specialty alloy? Is it viable to do that?
Absolutely viable, and you've described it very well. The commodity alloys need large plants with heavy expenditure. Specialty alloys need small plants with less expenditure, but very focused execution. Right. I'll give you an example. In motors, right? There's a group in IIT Madras that is developing an alternate to sheet steel that goes into motors, the stampings that go into motors, because for high frequency motors, you need very thin sheets. And those thin sheets, about 0.2 millimeter in thickness, are not made in India. Right? Everything in a motor, from magnet to sheet, is imported. Right? But there's a group here which is thinking differently. It's thinking, why not replace this sheet with coated powder, which is even less in diameter? And that powder can come from the steel plants of India, from waste of a steel plant in India, right? And that product can replace imported steel. But you don't need a huge steel plant to make that. For that, a startup is being set up here, and that startup will be the core, which can grow into an MSME to produce the material for the stator of electric motors. So to make high-end alloys, to find high-end materials and metals for specific use, you don't need huge investments and huge plants. These applications can be done in a focused manner by small companies.
So these would be obviously very profitable companies when they are built out and they're able to meet the quality standards. I presume that's the biggest challenge in some way, consistency and quality standard. And they would be an asset for the country and continue to be profitable for a long time. I think that's a great space to help our defense sector, our aerospace sector, and as you said, even a broader consumer electronics sector, consumer electricals sector. Let's talk a little bit about for a few minutes about stainless steels.
Sure.
And why are stainless steels important for any country? What are the sort of specific steels that I think we need to be worried about given the geopolitics?
Yeah. So stainless steels, from definition, is stainless, which means it doesn't corrode, and it has certain alloying elements such as chromium, nickel, etc., which create a very impermeable layer on the surface, which prevents oxidation of the iron and therefore retains its sheen, and it can tolerate different atmospheres or ambient conditions, right? So the use of these steels are in areas where you have corrosive environment, in chemical plants, for example, in high temperature, high corrosive atmospheres in power plants, atomic energy plants. Even people use it in railways. Railway carriages, for example, or you can say wagons, which carry certain materials such as, say, even coal, right? Coal in India has sulfur. So wet coal carries a lot of sulfuric acid. So you can imagine the life of those wagons that carry coal.
Sure.
It's 1/5 of their rated life.
Okay.
So it will help hugely if even there is a stainless steel cladding on these wagons. And many countries use stainless steel wagons or even stainless steel coaches to prevent passenger coaches, to prevent corrosion and from an aesthetic point of view. So corrosion resistance, prevention of attack from acids, high temperature, and aesthetics, stainless steel.
Wonderful. Let's switch gears away from metals
Yeah.
talk about non-metals.
Yeah.
What are the critical non-metallic materials
Mhm.
that we should be worried about?
Um, the first and the largest use is, I think, silicon,
Sure.
right? Um, and if you look at the widest use of silicon today, other than semiconductors in solar cells, right? India really struggles to produce solar cell panels, manufacture them at the quality and quantity needed, at the cost that will make it comparable to the rest of the world and competitive. So silicon dioxide is abundantly available. But then the process to get from silicon dioxide to metallurgical grade silicon, which is a carbothermic reduction process, and then chemical processes to get to successive additional 0.99s in silicon purity, is a very high technology, high level of technology, and is a patented process across the world. Unless India develops its own patented process, which is, I don't see it happening because there's no research going on the silicon part. There's alternative research going on, which I'm going to talk about. We are playing on pure silicon as for solar cell solutions is a game, I think, that has already gone past us.
Okay.
For India, I think what we need to do in solar, because solar is in,
Yeah.
right? We cannot be dependent on another country for solar cells. There are other materials that we can play with, and make them more cost effective and competitive to silicon, right? Such as perovskites.
Yeah.
Right? So I think there is a huge arena in front of Indian researchers, Indian academics, to develop solar cells which go beyond silicon. Yeah. The market is open. The market is huge. I just read today that about 37% of India's electricity now is renewable.
Sure.
A large part of that is solar. Right?
And hydro, probably.
And hydro. But the growth will be more in solar. Growing hydro is
impossible.
It's
Nearly
huge.
impossible. Yeah.
And we don't have good quality wind.
Sure.
So solar is what is going to cover from the 37%, the remaining 63%, largely.
And nuclear. Yeah, let's talk about that. So that's another materials problem, isn't it?
That's a materials problem, which thankfully, largely, our atomic energy group has sorted out. Right? I think the growth there will be in making micro nuclear installations popular, which is more of a regulatory issue, allowing whether government does it or you allow public sector to come in and play in that arena. But materials wise, the technology that we will use for fission, we have sorted it. And I mean, atomic energy has sorted it.
Sure.
That I think we should show as an example of what we can do by ourselves. And if we can sort that out, we can sort everything out, including solar cells, photovoltaics. But the future of atomic energy, popular atomic energy, democratized, is in allowing micro installations more popular, being more prevalent, which would probably need public industry to come in.
And then comes ceramics.
Oh, yes. Strangely, whenever you touch any advanced material, India doesn't seem to do much in it. Right? We have not been doing much in nickel. You mentioned nickel.
Yeah.
We haven't been doing much in silicon. We buy the solar cells and we convert them into panels, but we don't make the solar. We don't make the ingots, right? Ceramics, again, is a case in point. The world makes a huge use of ceramics. They make a lot of ceramics. There are large companies in ceramics, not India, right? Whether it's ceramics for medical, whether it's ceramics for aerospace or for machines, India is behind the world in ceramics. But imagine orthopedics operations. All orthopedic operations need medical grade ceramics.
Yeah.
Hydroxyapatite, calcium phosphates of various nature and forms. We don't make medical grade hydroxyapatite at commercial levels. We import, right? But good news is that we are waking up to it. There are some small companies that are coming up in the startups and MSME sector. You mentioned my venture capital fund. We are just funding a company in advanced ceramics in the medical sector.
Wonderful.
Yeah. So I think India will grow in the medical sector. And again, India can easily be the manufacturing ground for medical ceramics for the rest of the world. Yeah.
Their raw material is not a problem.
It's not a problem.
Process is the problem.
Process is the problem. You need to make it medical grade, right? And it can be done. And this company we are investing in, they've shown it can be done.
Okay.
And it needs young people to come in, believe in it. And there are, I think, today people who are going to fund these deep tech ideas and startups. Yeah.
On a related note, that's a bust of Pandit Madan Mohan Malaviya, made of ceramic.
Yeah.
It was gifted to me at one of the Ceramic Society meetings.
Right, which was held here.
Yeah. And I hold him in high regard for not just what he did for academia, but also what he did for ceramics at a time when it was probably not fashionable to talk about it.
They had vision.
Yeah. So let's come back and talk about the upheaval that is happening in the manufacturing side of things. Subtractive manufacturing is becoming slowly a thing of the past. We're now talking additive manufacturing. Gas turbine engineering parts, which are some of the most precision engineering parts, are today being additively manufactured.
Yeah.
How does a material scientist or a metallurgical engineer position himself or herself for this change?
Yeah. And let me step back a bit.
Okay.
Right. And I said at the beginning, or sometime in the beginning, that material science and metallurgy, they develop solutions for problems in the world, right? And therefore it needs to be holistic, right? So additive manufacturing was developed as a solution to certain problems in the world, right? It was realized that machining, subtractive machining, can go only so far. If you want to build lattices of intricate nature in an object, subtractive machining just can't do it, right? You need to build bottom up those structures. I think this came to real life when one of the aerospace companies, GE, to name it, had to reduce the size of its engine to get more clearance from the ground, and they had to play around with the fuel inlet nozzles, and the solution that they found was those need to be built differently, manufactured differently, right? The material scientists came to the table with their solutions. They didn't machine out the nozzle, they built the nozzle additively, and they could reduce operations, they could reduce welding, joining operations, they could reduce number of parts, and they could simplify the supply chain.
So it's not just about reducing the number of unit operations, but it's about fundamentally changing the structure of the part, of the metal in the part.
So now you're not taking a casting and machining things out, you're actually welding things into place. Because you're laying one layer after the other. And every time you lay one layer, the previous microstructure changes. You're making changes because there's a heat treatment every time you laid something out.
Sure.
Yeah. So yes, the fundamental nature of the material is different, right? And that leads to a completely new, almost a new field of study of the same nozzle is now a different material in a way. So that needs different studies, different even quality control measures, and new ways of looking at materials for a particular use, right? So while in the previous way you could design for the structure and machine things away, it's one microstructure. Here you have to actually develop a dynamic microstructure while laying one layer after the other. People have been doing additive manufacturing for ages. You know, I presume you've heard of hard facing, and it's when hard particles fall against some sheet, as in say a blast furnace, or in mining, you often throw stones, huge quantities of stone against a plate that wears off. And in order to prevent wearing off, you hard face it with very strong and hard substance. You just weld it and just put some weld layers on it.
Almost like friction stir.
Almost like, yeah, but you just layer them up with this. So people have been doing this, and it's a metallurgy of putting these layers upon layer upon layer, and making sure that this new structure is robust. Because every time you do a casting, it's like a casting. You don't have unwanted microstructure because of the heating cycles. It throws open an area of study which earlier didn't exist, as to making sure additive manufacturing is a solution that will remain and will grow in the world. That comes the background material science of metallurgy to making sure that these structures are robust.
How are we doing with additive manufacturing technology itself in India? Are people making these machines here? Is that technology available to us? How are we faring there?
There's a growing movement in additive manufacturing in India. We started late. But here in IIT Madras, there are groups that are doing additive manufacturing in the medical sector, in the defense sector. Even in our metallurgy department here, there are examples. MeitY, the Ministry of Information and Electronic Technologies, they have put up institutes on smart manufacturing that includes additive manufacturing. And there I can see that there's huge encouragement that is coming to startups and SMEs that are building machines in this area. They're building material that is amenable to additive manufacturing, because that's another thing you to do. The powders and the wires that are meant for additive manufacturing need to be available, and there is ability to create the design and the inspection and ensure robustness of additively manufactured components. So that ecosystem is building up, and it's a combination of various laboratories, academia, and some industry that's coming into it.
Another sector of material science / metallurgy is interfacing materials. You alluded to welding earlier.
Yes, that's right.
Right? I was talking to somebody yesterday about another topic related to railways, and they said all railway system failures the vast majority of them are attributed to interface failure.
Right.
How are we doing with understanding interfacing in India? Or again, welding, similar, dissimilar,
Correct.
It's a massive field and opportunity, isn't it?
The biggest area where interfaces play a role is in composites.
Yeah.
Composite materials, right? So imagine it's like HAL uses carbon fiber composites.
Yeah.
Right? There's carbon fiber and there's a resin, right? And the integrity of the structure will depend on how well the carbon fiber bonds with the resin. The carbon fiber has strength. The resin is the matrix. If the interface fails, the plane falls. Right? So this interface study is extremely important. And the knowledge and understanding of the interfaces, and then to design the interfaces to the need of the user is extremely, extremely important. Not only in aerospace, but as you said, wherever there is welding. Luckily in India, I must say that understanding of weld failures and welded structures and robustness of welds is quite mature. And we have
Okay.
multiple institutes and both academic and laboratory, and organizations such as BHEL. They're extremely good at understanding welds. I think in the years to come, when India grows in composites, that's one area India hasn't grown much in. India does not produce any carbon fiber, for example. It imports all the carbon fibers that we will need for aerospace. We need to put effort in both the fiber material and also interface studies between the fiber and the matrix. Yeah.
Again, these are all fields of study where if one specializes, they become very valuable to any organization.
Absolutely.
That they will be associated with. Let's talk a little bit about industry demand and career trajectories for in this space of in all of the spaces we talked about. Typical starting salaries at a steel plant, a steel company, at an engineering level seem to be between 4 to 9 lakhs, somewhere in that ballpark. But as one specializes, the growth is somewhat non-linear. What would be the argument to say, look, here's a space you can come make a difference to the country?
My message on that is actually very simple, and it alludes to one of the stories I was telling earlier about Tata Steel. You don't work for the salary, because salaries change. Right? Salaries change with time, salaries change with companies, salaries change as you go up. It's important to know for a youngster that what really matters is the pride and pleasure in the work, right? Unless there is pleasure in the work, no matter how much salary you get, it won't matter. And if you have pleasure in the work, an average salary will do very well. And if you have pleasure in the work, your salary will increase because you will do well, and that will be recognized, and you'll move up, and your salary will move up, right? So from my personal experience, I stayed with doing what I was doing in the company that I was in because I loved my work. I loved the environment in which I worked. The rest was a result, right? And I really never have looked at my salary slip. Yeah, and I wouldn't change the company for anything, right? So I think if you follow the passion, my message is, if you follow your passion and do what you love, the rest is a result.
As opposed to 30 years ago when you started your career, today we discussed already several opportunities where somebody can follow a passion, say create a specialty alloy startup company and reap the upside as well.
Absolutely. There are more opportunities now than we had when we were young.
Yeah. So I think this space of material science, creating materials that are use inspired, that would that would solve a problem, in your words, is also a space where salary may be one form of remuneration, but risk starting up and reap the upside yourself.
Absolutely.
I think what would be the 1 minute pitch to a young scientist in the space of metallurgy?
Right.
What are the research opportunities in this space?
Right. So to the young scientist mind, right? The young scientist, civilization is based on materials. And the progress of civilization needs material solutions to be developed. In the Iron Age, we've grown from one steel grade to the next steel grade to specialized alloys in steels for all sorts of uses, including bridges, railways, armaments, aerospace, etc. In the electronic age, in the silicon age, we will grow from silicon to germanium to gallium. In solar cells, we will go from silicon to perovskites to other materials. The growth of civilization is in the hands of material scientists. So if you're committing yourself to research and development in material science, you're committing yourself to helping civilization grow. Welcome to material science.
That's absolutely fantastic. Let's finish this conversation with what AI can do. We promised we'll come back.
That's right.
So let's do that.
You stopped me then. Yes.
The library of materials that are available for a product designer today is just mind-boggling. I mean, there's no way any single person can keep track of this library.
Correct.
Clearly, the field is ready for a tool,
Right.
something that will parse
Absolutely.
this problem for the engineer.
Yes. Traditionally, product development in materials involved creating a table and doing a complicated and a vast series of design of experiments to come down to some 3 or 4 alloys which you would then melt and take forward, right? It needed time, patience, money, and manpower. First to generate data and then to sort out, right? But now there's enormous amount of data, and large part of the data is now available on the internet, right? Even 5 years back or maybe 7 years back, that data needed to be structured to be accessible. But with the advent of LLM, even that need has gone. I mean, it can access data in whichever form it exists largely. The crux, therefore, is that AI and ML can and need to be used to access this huge data bank that exists in literature today in various forms, and use that data to reduce the time, manpower, and money needed to do extensive experiments, to narrow down into select chemistries.
Mm-hmm.
What needed maybe 6 months of literature review and 1 year of small experiments can be done over a few weeks now. To use AI/ML to sort out, to screen out various patterns in the data for the use case. And looking at those patterns, you can, within a few weeks, you can select specific chemistries to do those final tests. So I think a time span of 1 year to 1.5 years can come down to a few weeks now. And I can see that there was efforts in this direction are already afoot. Materials genomics was inaugurated by President Obama. Has gone some distance. A similar effort was initiated in India under the auspices of the Indian National Academy of Engineering, and it has gone some distance. And now, to my surprise and pleasure, I can see startups coming up in this area that are using AI for product development. And those startups are not only in UK, US, they are in India.
Wow.
Indian startups proposing solutions for product development.
Can AI be used to design an alloy for a particular use case?
Absolutely. Absolutely, it can. It can help the researcher to narrow down from multiple options. And it's then up to the researcher to do very quick tests on those options. So AI can definitely be used. I've myself used that to narrow down options for alloy development for a particular use case. Yeah.
So this revolution that we are seeing around us with data science permeating various disciplines of engineering, again, promises to change the field of material science as well.
Yes.
And the opportunity for a young material scientist there is to also be trained in the tools of AI.
Yes.
Alongside being a formal metallurgist and a material scientist, to be ready to harness the full power of these tools in their profession.
Yes, I would just change the perspective a little. It is important for the material scientist to be trained in AI.
Yes.
Because you can't train a data scientist in material science.
I have long argued for that. Yes. I think each professional engineer
Yes.
should graduate with their professional engineering
Yes.
degree and also
And-
be trained and well versed
Yeah,
in the tools
absolutely.
of AI.
Yeah.
One does not need to know what's under the hood,
No,
in AI.
there are specialists for that.
They're specialists, exactly. Good. I'm glad we agree on that. The last question I have for you for today is, where is the world headed with sustainability? Steel production is still a massively carbon emitting sector.
You say that's the last question for today? That's almost like the first question for the next session. Because this can't finish in an hour.
Yes, we will come back. We will promise to come back.
But to give you a very quick answer on that one, as almost like a trailer for for our next session of sustainability, metal manufacture, metal extraction. The crux is to take oxide out from the ore, right?
Yes.
Most ores, whether it's aluminium or iron, they are oxides. So you have to take oxygen out. Now, for iron, which is the largest metal that is manufactured in the world, 1.8 billion tons, the easiest way to take oxygen out is by reducing with carbon. Carbon dioxide is formed. To the extent that in the traditional way of making iron from iron ore using blast furnace, roughly 2.5 tons of CO2 is given out per ton of steel.
So that's just the chemistry of the reaction.
That's just the chemistry of the reaction, right? So it's like it's a carbon dioxide producing industry with steel is the byproduct. I'm not going to be very popular saying that, but it points out the difficulty.
Yes.
That the next close reductant is hydrogen. But hydrogen is expensive. If you produce hydrogen using electricity, unless that electricity is green, you just move the CO2 problem upstream.
Yeah.
You've not really solved the CO2 problem. Green hydrogen is still more expensive. Right? So unless the cost of green hydrogen comes down, that means the technologies for electrolysis improve. We find new materials for catalysts for these electrolyzers, underlying materials.
Can't run away from them.
Can't run away from them. You will not be able to get hydrogen at a cost that is affordable to produce, to get rid of CO2.
Are there commercial, so quote unquote, green steel manufacturers in the world today yet?
Yes, there are. So green steel is a nomenclature. Yes, what is green steel? I mean, you can reduce the CO2 footprint from 2.5 tons per ton to 2 tons per ton to 0.2 tons per ton. Where do you say it is green, right?
Okay.
Net zero is almost a myth, because even if you press the steel to a form, you need energy, right?
Yeah.
And unless that energy is green, it has a CO2 footprint. Even the grease that you use, so the lubricant that you use, has a CO2 footprint. so net zero is mythology, but there can be a number, right? But we'll go away from the didacticness of this. We will assume green steel means a substantial reduction in CO2. There are some plants in the world which produce very small tonnages that use, say, local hydroelectric power. So in the Scandinavian countries, power is hydroelectric, and electricity-based steel making. That's largely green.
Okay.
Right.
So they're practically electrically dissociating the oxygen out of the ore.
Electrically producing hydrogen and then using the hydrogen to reduce.
Okay.
Electricity-based reduction of iron oxide, people have tried and are still trying, is extremely difficult to scale. Right. But in the Middle East, they're trying hydrogen-based as well as largely reduced C component through methane. So natural gas has CH4. For every 4 units of hydrogen, you've got 1 unit of carbon. But then if you can use both carbon and hydrogen for reduction. So that substantially reduces carbon footprint and partially green, therefore. So there are plants that use natural gas, plants that use green electricity to make hydrogen and then reduce. But solutions for India are going to be different.
What I'm taking away from today's conversation is no one technology can be developed in a silo. We
Correct.
talked of green hydrogen, sort of segueing into producing greener steels for us. More efficient production requires other forms of technology. We talked of additive manufacturing, borrowing from other fields as well. I think this is a field that is strategically important for the country and absolutely rewarding in by every definition of the word reward, for a young man or woman to step into and make a difference to
Absolutely.
himself, herself, and the society around us. Debashish, this has been a wonderful conversation. Thank you so much. As we promised, we'll have to come back again and do a part two.
Thank you, Mahesh.
This is a field wide enough, broad enough, that I think we need more attention to this discipline for sure.
Absolutely.
I hope you all enjoyed it as much as we enjoyed the conversation. This podcast is brought to you by IITM Global, an initiative of the Office of Global Engagement. You can learn more about what they do in the link in the description. This is another episode to help you make informed career decisions. Learn what's happening in each discipline and then decide where you want to go. As we say, this is your future simplified. Until we meet again, be well, do good, and keep in touch. Goodbye. Namaste.